Good evening, all of you. Especially thanks for joining today. It's Ganesh Chaturthi. It's holiday, and still you have joined. Welcome for today's session. Today is 8th session for this Smart Grid Basic to Advanced Technology course. We will follow the same agenda we have been following. We'll see overview of week 8, and then we will discuss some questions, and then have your doubts. So these are the deadlines for assignment 8 and 9. So I think I have made a mistake. It's September 27th, not 21st. And the recordings of these online lectures are already available. You can access them. We would like to start with the overview of week 8. In week 8, some good important topics were discussed, like starting with the PMU placement and then cybersecurity, which is very important, especially when we are talking about smart grid where everything is governed. A major component of smart grid is communication network. So cybersecurity becomes a very important and a vital issue. And then virtual inertia, ancillary support, demand side management, and demand response analysis. So these were the topics which were covered in week 8. We will see them one by one. Starting with PMU placement. So why do we need to do optimal PMU placement? We can put PMU at each and every bus and measure all the variables, but that will be very costly because PMU is a costly equipment. So we cannot always, we want to minimize the cost whenever we want to plan, we want to operate the system. For that purpose, we want to minimize the cost. So is there a way where we can reduce the number of PMU and still we can estimate the state for the entire system? That is the idea behind having optimal number of PMUs. And because in the uncertainty in generation, because of increasing penetration of renewables is increasing, and also earlier, until now, demand we used to consider it was not that variable because based upon historical data, there was only a slight variation in demand. But now, in future, because of these electric vehicles and more electrification of the entire industrial sector, all these things will make the demand more uncertain. So in future, it will become more important to have a real-time monitoring and control over these generation and demand balance, especially in the distribution system. So for that, we need data, measurements, and we need PM. In distribution, we have micro PMUs. So we want to place them at minimal number of buses and still want to know the entire state of the system. That is why we want to have optimal PMU placement. So the method which was used in the slides in the lectures was based upon DC power flow. It's a linearized. Actual power flow is AC power flow, but that is non-linear because we have sine and cosine terms in the actual power flow. Just a minute.
Is it used for AC systems, sir?
Which one?
DC power flow.
Yes, we use it for AC. It's an approximation of the AC power flow.
So it is used for AC and DC. Am I correct, sir?
Yeah, it is used for AC also.
AC and DC, both it will be used. Am I correct, sir?
This is for AC.
Okay.
This is
For
for
DC
AC.
system,
This is because delta is not in AC, DC. So this is only for the AC.
okay. If
Yes.
DC distribution system means how we have to do for optimal locations. DC
That-
microgrid systems are there, In that situation, what methodology we used for minimizing the PMU?
Then the equations will change. The governing equations will change. Here the equations are different, there the equations will be different. So only equations will change. Objective function will still remain the cost minimization for power flow.
Okay.
Even objective function, it depends. Here we have taken a very simple objective function has been considered, but in practical scenario, even the objective function can be quite complicated. There can be several things which we want to minimize. So we want to minimize loss also. We may want to restrict the emissions, carbon emissions. We may want to restrict the deviation in real time. So there are several things which we can combine in the objective function. So here the objective function is only the operational cost of the generators. So and that
Okay, sir.
here
Concludes, linearized DC power flow controller is used for AC system, not for DC system. Am
is
I correct, sir?
because yes, correct, because
Yes.
this linearize is because actual AC power flow is not linear
Yes.
because we have sine cosine terms, right?
Yes, sir.
Will we have B sine delta 1 minus delta 2. Similarly, cos term also will be there. So these are non-linear terms. And when we use non-linear terms in optimization, then the techniques will we have to use non-linear optimization, and that is difficult to optimize. Although that we'll discuss further also. But here, main thing here is right now we are minimizing the operational cost with respect to certain constraints. So these are our constraints which we always want to satisfy. So what is this constraint?
Flow.
Real power generation and real power demand.
Yes.
Sir, one more doubt I have. If the linearized DC power flow control is used for AC system means, in that constraints, there is no equations for reactive power side,
Just a minute. I think this fan is creating noise. I will just switch it off. I will just come.
Okay.
Yeah, because that is the assumption which we have made. In AC power flow, there will be equation for both active and reactive power. But when we make assumptions, we assume that the reactive power is not there. So it's only real power is there. And also there is no frequency because it's DC.
No, I think because the cost is always related with active power, so that is why reactive power is not included. This is my thing.
Actually, there are 4 assumptions which are made when we want to in the actual AC power flow. Using those 4 assumptions, we get only one single equation for this active power. Then reactive power is neglected because of those 4 assumptions which we make. So DC from AC to actual AC power flow to this linearized version of DC power flow, it's based upon the 4 assumptions which we make.
What are these 4 assumptions?
So one is we consider this difference in angles to be almost 0. They are very small. That is very small. And that is why sine of delta 1 minus delta 2, it becomes equal to delta 1 minus delta 2. That is why here we see this term delta 1 minus delta 2, delta I minus delta j, because we are considering that these angles are very small. So if they are very small, sine of theta will become equal to theta. Next, another assumption that we make is we consider all the voltages at all the buses are equal to 1 per unit. So VI are equal to 1 per unit, close to 1 per unit. So in practical system, they will be very close to 1 per unit because we want voltage to be regulated. It will be close to 1 per unit. And another assumption is R is much lesser than X. R by X ratio is very small. And because of this assumption, Q is also neglected because of fourth assumption. So these are the four assumptions that we make, and this results in this linearized DC power flow. And that is why this power at each node becomes only delta 1 minus delta 2 by X.
First is delta is small, second is voltage is 1 pu, third
Yes.
is R is very, very less than X. What is the fourth one?
Fourth assumption is on reactive power. Yes, you want to say something?
Sir, in distribution, R cannot be much less than X. In transmission, we can say that R is much less than X. But whatever the
Yes.
smart grid is acting, in distribution,
That is correct. But this linearized DC power flow formulation is for AC, for transmission system. Because if we want to use for distribution system equations will change. We cannot neglect R.
Okay, sir. Okay.
That is true. Absolutely correct. So here it is. So this first constraint is at each node, at each bus, whatever generation is there and whatever demand. So we are subtracting generation minus demand. So net injection, which we are taking net injection. What is the net injection at that bus? That will be equal to power flow from that bus. Suppose we have a 3-bus system. 1, 2, and 3. And there are 3 lines. Here, generation, demand. So P1, P2, P3 is generated, PG. And similarly, PD. And these are Xij, X12, X23, and X13. So now if you want to write equation, this first constraint, then here we will say it's Pg1 minus Pd1, net injection at bus 1, which is equals to, so it's simply extension of KCL. So net injection is equals to net withdrawal. Withdrawal is here in these 2 lines. So it will be delta 1 minus delta 2 divided by x12 plus delta 1 minus delta 3 divided by x13. So that is why we have a summation here, this summation. Is this clear?
Yes, sir.
Then second, what is the second constraint?
Voltage is 1 per unit for all the buses.
No.
Line capacity.
Yes, this is line capacity. So we have defined here this delta 1, that power is equals to angle of difference of angle divided by the reactance. So this is equals to line flow. and this is same line flow. So we want the line flow to be within its maximum limit. Below it can be maximum equal to, or it should always be less than. So it's less than equal to P max, maximum line capacity, and in both the direction. That is why here we have negative. If we consider this direction from 1 to 2 as positive direction for line flow, and if the flow is on reverse direction, then it will be negative. So in reverse direction also it should not exceed its limit. That is why we have a negative here. And then the third one is
Generator capacity.
generation capacity limit. So if we do this, it's a very simple formulation, and this will give us what should be the generation at each bus, so that the overall cost of generation is minimized to meet certain amount of demand. Okay, so the output from this output of this linearized DC power flow is used here. Is PGI true value. This is the output from that linearized DC power flow. This we already know. Minimum and maximum demand and minimum maximum generation is already available. So here we want to minimize the cost of installation of PMU, where Xi is a discrete variable. It's a binary variable. It can be either 0 or 1. Either the PMU can be there on that bus, or it cannot be there. So if it's a 13 bus system, then there will be the X will be a vector of, so it will be vector of size 13 by 1. So for each bus we'll be having one X variable, and it can take either value 0 or 1. So these two first and second constraints are limiting the generation and demand within their limits. And second one is for angle. Angle should be between minus 90 and plus 90. And then the deviation from what has been calculated from the DC power flow and what we are calculating from state estimation, the deviation should not be very large. So we want to keep it within a tolerance. That is, these are the two constraints. And then next one is this observability constraint. So can you tell what is this observability constraint?
Sir, why the angle should be minus 90 to plus 90, sir?
What can be the maximum angle? Because generally it will not go for stability reason. If you would have seen this is the curve P versus
Yes, sir.
delta curve.
Yeah.
We always
At
want
90, it produces maximum power. Yeah.
Yes, we always want to operate below this.
Okay. Understood, sir. Thanks.
So who can tell what is this observability constraint and why do we need it?
So from one bus, how many other buses we can calculate is the observability. Like suppose if from one bus I can calculate 9 other bus, so that means the observability state is 9.
That means suppose from this, let's say this is bus 1 and it's connected to 3 other buses, and if I know voltage at this bus,
so from one bus I can calculate the parameter of all the 3 buses is observability.
Yes, we can calculate voltages at other buses if I know voltage and current at this bus. So observability, this constraint ensures that with minimum number of PMUs, we can observe the entire system. So this ensures that we want at least one PMU. At least one PMU. Because we are minimizing here the cost, so it will always take one. If you make it two, then it will give us more number of PMUs.
Is there any formula or some what you say method? Is there any formula or method to calculate how many PMUs are required in X bus? Suppose I have a 100 bus. So how many PMUs are required? Is there any formulas there?
There is no formula, because if there would have been a formula, then we would not have to do this. We would not do all this optimization. So because we want to minimize number of PMUs, and subject to, there are so many restrictions how we want to place them, and all these other variables which are affected by that should remain within the limit. So for that, we cannot do it manually. Maybe for a two bus system, a small system you can do, but still you will have to do lot of calculations for that. There is no straightforward formula for calculating the number of PMUs.
Like
That is why,
in this example, my bus 1 is connected to 3 buses.
yes,
It is direct connection, so that is why I can calculate the buses voltage of other buses. But
yes,
a situation where it is not connected directly, so then I think it is observability will not be possible.
yeah. So for that we need more number of PMUs. So suppose if
That is why one relation here is coming, that direct connection is the must for observability.
yes, because this bus, since it is connected to other bus, so if we have PMU at this bus, we can measure, we can calculate parameters at these three buses also.
Suppose from bus number 3, some another bus is connected, like bus number 5. So from there, one, it is difficult to calculate the bus number 5.
Yes.
Some relation, graph theory relation is coming.
Yes, that is correct. There are some graph theoretical methods by which you can, even for a small network, you can do you can use some concepts of graph theory and find out without doing any optimization. That will also give you a good result. Minimum number of PMUs, you will get the same answer. That is possible using graph theory. But if you want to use that graph theory method also for a very large system, then you will have to use some algorithm. Whatever steps you are following for a small 3-bus system, you will have to code it, because doing it for a very big system also will be cumbersome. So there are different methods. Optimization is one of them. Graph theory is another method. So we can use any of these methods. But for a big system, we have to use, there is no straightforward way to, there is no formula. So we have to use these methods. And in distribution system especially, there are so many consumers, so many customers, so many buses. There it becomes even more important to use these optimization techniques or other methods. And we are using this DC power flow method because we want to make the optimization problem simple. Non-linear optimization is difficult, and it also depends upon the initial condition that we give to non-linear optimization. So in classical methods there are several. So we'll see. It will come again. So I will tell there in subsequent slide. We will discuss these different classical methods. Then I will tell you why are we using these classical methods. What's the advantage of using the classical methods? So let us move further to cyber physical system. This was the next very important aspect for a smart grid. Cyber physical system is, you can divide this entire phrase into, so first part is cyber, second part is physical. So even before smart grid we were having physical system, the physical layer, all the generators, whatever system which we were having, generation, transmission, distribution, that was already in place. We have included this cyber layer, and together the interaction of cyber layer with the physical layer is being used to improve the performance of the physical system, the physical layer. So you can see here, so this is the physical system. So it can be, there are plants, different processes, actuators, sensors are also there. So from here we sense the data through sensors. So here sensors will be there. So these sensors will take such, let's say temperature data is there, or voltage, current data. These are analog data. So we have to convert them into digital domain, because entire control system that we use, all these things, most of the communication, it happens in digital domain. And all the processing which we do, they use all the computations, all the computers are based upon digital. They work in digital domain. So we have to convert them into ADC. Then after digital domain, through communication, it goes to control center. And then again, after taking certain control actions, we again convert the digital signal into analog, and then it is given to actuators, which will change the settings of the physical system. It may be generator. So it will it may open the turbine valve. So that can happen. So you can see on this side, it's more elaborately explained. So this is the physical system, same thing which we have explained here. This is the physical process. Through sensors, the data will sense the data and send it through via the communication channel to the control and computing center. It will do certain analysis and send the data back via the communication network, and through actuators again it will go to the physical layer. So this cyber layer has these three components. One is the communication network, then computing aspect, and the control system. So all these things will come under the cyber layer. So this is another representation. So this is our physical system. So we have different renewable generation. These are the interfacing converters. We have hydro, nuclear, fossil fuel generation, conventional generation, then transmission and distribution. So here through sensors information is acquired. So information acquisition, then through sensor it goes to, via this communication network it goes to the control center. And through control center again it goes via communication network, it goes to actuators and other devices which will change their settings. So this entire system is called as a cyber physical system. So these are different characteristics which are compared for physical and cyber system. So components here are generator, transformer, lines, and here we have three components: control, communication, and computing devices. Then the nature of system here is continuous, and this entire cyber system works in discrete domain. So that is why the governing equation, mathematical equations also changes. Here the flow of energy is there, and here we have flow of information. Similarly, other things, contingency, we can have generator line outage. Here also we can have cyber attack, communication latencies or delays, we can have malicious control impacts, all these things. These are the advantages of cyber physical system, that we can have two-way communication flow, two-way flow of information, which is very important for SWAT grid. And then we have efficient, safe and secure operation of power system, entire power grid. And the automation is also possible because of these sensors and actuators. But the major disadvantage is the cyber attacks. It is vulnerable to these cyber attacks. Delays in communication. Some package may drop out. There can be missing data, loss of data. Network jamming, congestion, which we experience sometimes when we call someone. Then sometimes we are not able to connect because network is congested. Or sometimes what will happen, I've called one person, but the call will actually go to some other person. So all these things happen when the network is congested, communication network is congested. These things are a disadvantage. So these are examples for the cyber attacks which have happened in from 2010 to 2021. Especially on all these are for power system. So you can see entire power system and control center failure in US and Germany, 2019 and 2020. So these can be very dangerous for the power system. So here you can see black energy attack. It led to widespread blackout in Ukraine in 2015. Again, here power distribution system failure happened in Ukraine in 2017 because of this WannaCry ransomware. Here also ransomware attack on energy generators. And this is latest for India in 2021. Red Echo. 10 power assets were affected. And some ports were, operation of ports in Mumbai and Tamil Nadu was also affected because of this. So the more we rely on communication, we have to make it more secure. And it should be able to withstand, detect cyber attack and still operate. So these are different types of data manipulation attacks or cyber attacks. So what's the full form of FDIA? So this is false data injection attack. Yes, correct. So this is, then DOS is denial of service, and MITM is man in the middle. So FDI is very, any kind of cyber attack is not good for system, but here you can see the major difference between these two is, here whatever service was being provided, that is still being provided, but because of false data, the quality of service will change, it will degrade. Suppose the attacker changes the data, or we use PMU for measurement, for voltage current measurements, for acquiring these measurements. If someone changes the synchronization, the time, the clock of the PMU, then the data which is reaching the control center, the time stamp which is attached to that data will change. And suppose at the voltage was at 10:00 or the voltage was 230 volts, and 10 hour 15 minutes it was let's say two, it's something 250. It is saying it's 250. Actually, it was not 250. So this is because the timestamp has been changed. It might have been at some other time, but the attacker may change the timestamp, or the attacker may even change the value itself. So that will lead to different outcome, and the decision which the operator has to take, that will change. Suppose the actual load was 100 gigawatt, and because of the false data, it is showing that the load is only 98 gigawatts. But actual load is 100 gigawatts, but false data is showing it as 98 gigawatts. So what should be done? Generation should be reduced or it should be increased?
It should be increased.
No. False data is saying that load is reducing. Earlier it was 100 gigawatt. Now it is saying the load has reduced, but actually it has not reduced. So as per the false data, the generation should also reduce, because we want to maintain the frequency. If overall load is 98 gigawatts, the generator should also be close to it. Correct? But actual demand is 100 gigawatt, and if I make the generation 98 gigawatt, there is a mismatch, and frequency will deviate. So there can be very different decisions because of these false data, and these can lead to cascading failures, even blackouts, which have happened in past. So that is our entire state estimator. It depends upon input from these different measuring devices, and if there is any kind of false data injection either at the level of sensors or controllers or in the communication channel itself, then the decision which will be taken, which is taken to make the system stable, to keep it reliable, to keep it within the limits, it may not be in the limits because of these false data injection. So that is why it's very important to detect these false data, any anomaly in the data, and then mitigate it so that system can still work in its normal condition. Or if there is a problem, we have to remove the faulty section. So this is the false data injection. Then this another one is this denial of service. So here the quality of service is being impacted, but here denial of service, even quality, there is no service itself. Service is not provided. That's why the name is denial of service. And this can be because of two things. Either communication link is suspended, or the second one is man in middle. Someone else is there eavesdropping. Suppose you want to access a site, and you have entered the URL and assuming that this is a site which you wanted to access, and you have entered your entire details also. But actually that site is not the one which you want to open. It is actually directing to someone else, because there is someone else in between who is trying to take the data from you. So that is why, because someone else is there in between, the service will not be provided. And because the communication is in both the direction, So this person can be here also. It can impact both the way. From control center to physical layer or from physical layer to the control layer. In both the way, this can be impacted. So actual data will not even reach there. Is it clear?
Yes, sir.
Okay. So this is example of this false data injection. So here is the distribution control center and distribution state estimator, which is used for capacitor switching, feeder reconfiguration, and demand side management. And this is SCADA power. This is the main grid. And then we have these different. This is the distribution. This is the different field devices or our sensors, and these are the feeder buses. So the attacker can attack at these different stages. It can attack in these devices. It can attack in this. So this is the communication channel. So communication channel can be impacted, or even in the control center, either in the SCADA system. So all the three, the attacker can attack at any of these. All these are vulnerable points in the distribution system. Similarly, in the transmission system also. So for that, we use different types of techniques. Here you can see FDI threats can be at these levels: end user level, field devices, control center, and energy pricing and trading. And these can affect all these things: voltage regulator settings, PMU management, IED data, volt var control. All these things will be impacted. So many vulnerable points are there. We have to make the entire system secure against all of these. These are the impact of cyber attacks. So economic impacts is the first one, it's easy to quantify. So it can affect the load forecasting, and that will change the estimated state, which will affect the day-ahead market. So for the next day, we always use the forecasted demand, and based upon that, the entire day-ahead market works. When scheduling is done, and then physical impact, there can be changes, impact on the transient and steady state stability, voltage control, impact on the frequency control, as we saw that example. When false data injection is there, the actual generation and demand may not match, and that will lead to frequency deviation. These are different attacks on state estimation, voltage regulation. So let's move to cyber security and resilience. So cyber security means we want to protect against any kind of these attack, any threat from cyber crime. And resiliency, the main, we have the cyber and physical layer. So we have three things here. We have physical system, we have cyber system, and communication. Communication is a part of cyber only. So we have to make all these three resilient. So much work is being done to make the physical layer resilient, especially in these European and American US power grid, because every year they are facing these extreme climate weather events, these forest fires, earthquakes, hurricanes. They have become very frequent. Their frequency have increased, and that is creating lot of problem for the entire power grid. And so much load is lost every year, and that is creating so much economic loss. So that is why resiliency has become very important in past few years. Do you want to mitigate the damage and carry on the system and remove the data which has the system which has been compromised and still work, isolate the compromised part? It is also called the ability to bounce back. How quickly we are able to regain or again restore the power to restore the power back to the loads if there is some fault or some deviation is there, disturbance is there. So in simple terms, it is called, it's to adopt, to first of all anticipate, then mitigate, adapt to it, and also provide corrective measures so that we can quickly bring the system back to normal. So all this is a part of resiliency. So these detection techniques for cyber attacks are of two types, centralized or decentralized. And all these are mathematical techniques. So state estimation for centralized, it's based upon the data. It's data driven. It depends upon the entire state estimation. All these things are dependent upon data. The chi-square test, it's a test to determine the bad data in the entire data set. So it can detect that this is a bad data. So it's a mathematical or probabilistic approach. Then there are residual based methods and model free, which are machine learning or statistical methods. And decentralized methods are immune to these, even incomplete measurements. They can work with incomplete measurements or even with noisy measurement. There are these methods like singular value decomposition and observer based method. So it's a control specific method. And this is also in mathematics we use this. Have you heard of the singular value of a matrix? So it uses that concept of singular value decomposition for a matrix. So entire network, and the data which we have, we use it to calculate the singular value, and then based upon that we can determine whether there is a anomaly in the data or not, whether there is an attack or not. All these are different methods which we can use. Then the next topic was virtual inertia. So what's the need of virtual inertia? First question, very important question is this. Why do we need virtual inertia? Why are we talking about virtual inertia?
To balance power generation and power demand.
So was it not required earlier? Why are we talking about it now?
See, like photovoltaic generation, they don't have inertia. So that is why with this renewable energy, virtual concept is virtual. This is concept is coming. Virtual inertia concept is coming.
Correct. So earlier we were having these conventional synchronous generators, either hydro, thermal, nuclear, or gas. All these are rotating machines. They have a generator. So these are big rotating mass. And these rotating mass, they have this inertia. So every mass has an inertia. And because of that inherent inertia, the small fluctuation in load, in demand, they can meet that fluctuation in demand because of that inherent inertia. That inertia can provide that demand. And it's very quick. The inertial support is very quick. Within few milliseconds also it can provide that support because of the inertia present in the rotating mass. But that is not possible for these inverter based DGs. So virtual inertia concept is to mimic the conventional synchronous generator dynamics. The way they provide synchronous inertia, we want these inverter based DGs to provide the inertia. Cannot provide in the same way, but we are doing something, we are modifying the control of these DGs so that they can provide a virtual inertia, so that their control is modified in that way. And what is the source of the inertia in these generators? It is the short-term energy which is stored in the DC link capacitor. So DC link of these converters. So that is the source of the energy. For the conventional generator, the source of energy is the kinetic energy stored as inertia. So the inertia stored in the conventional generator is converted into kinetic energy.
The capacitors, supercapacitor are the best for this inertia.
Yes, supercapacitor, even other supercapacitor can provide this inertial support. That is possible. Even this battery can also provide a supercapacitor and flywheel also, because they are very quick and their power density is high. So that is correct. Then the next concept is of this virtual synchronous generator. It also enables the converters and DGs to mimic the behavior of this conventional synchronous generator. So it can provide this inertia, frequency response, and voltage support services. And we can also tune them by doing certain adjustments. So this is now we are moving to that last topic of demand side management and demand response. So this is a typical curve. This is for February 2020, 17th Feb. This is the All India demand map. And these are the regional demand map. For different regions, we have 5 regions. And this is the All India generation. So you can see yellow is the solar generation, solar PV. And red is the total generation. So this is thermal. Then we have this gas. This is hydro. This is wind. So wind we can see it's almost throughout the day, and especially more during these late evenings. Here we can see. So that is why one of the I think there is one project which is integrated it's in Andhra Pradesh. So they are using it is being it's under construction. They have a pumped hydro storage and wind as well as solar. The availability factor or the capacity utilization factor for wind. So have you heard of this term, capacity utilization factor or availability factor? Anyone?
Capacity utilization, I have heard. If correct me if I'm wrong. Capacity utilization means suppose you have an installed capacity of 100 megawatt. So how much capacity you are using, like 50 megawatt if you are using, 80 megawatt you are using, like that. So capacity is always greater than what you are using.
Yeah, so that is correct in some sense. So it's also called availability factor, some and capacity utilization factor. So if we take the conventional generator, if installed, it will always be less than the. It's a fraction of the installed capacity. If we have an installed capacity, then for conventional generator, if we remove the forced outage rate, let's say it is there are some outages 2%, 5%. It's always for conventional generator. It this availability factor is around point. It's more than 0.9. It's around, let's say, 0.9. So that means the point 90% times it will be producing the installed capacity. It will be available. But for the solar and wind, if the installed capacity is 100 megawatt, it may not always provide, because we can see here solar is available only during this from 7 to 6, 7 a.m. to 6 p.m. So rest it is not even producing. Although installed capacity is there 100 megawatt, it is not producing. So the average over the entire day, or we take it over annual, monthly, annual, we can calculate these utilization factors. It will be a fraction of the installed capacity, and for individually for solar and wind it is less. For new installations for wind it is around 30%. But if we combine these two, solar and wind, as a hybrid power plant, then this utilization factor can go up to even 40%. Because we can see here also, from this morning 7 to 6 p.m., solar is producing, and even wind is there, but wind is also available before and after this duration. Wind is even higher in late evenings, and that is why we want to even go for offshore wind farms, because that wind is steady and even wind speeds are high. So this output will further increase. So this project is a pump, this hybrid project. They have a storage also and combined wind and solar plant. It's under construction in Andhra Pradesh. I'm not remembering the name of the project. So here you can see this is a peak. If we take the average, it will come out somewhere here. This much additional peak is there, and the generator required here, they generate only this during this period. They are not generating during this entire duration. For meeting only for few hours, we have to maintain such a high install capacity. So if somehow we can reduce this, because our demand is increasing, every year it increases, because we want to electrify more and more. Electric vehicles now they will come. We want to electrify our industrial processes also. Even the air conditioning requirement, heating requirement, all these things are increasing, so demand is increasing. And if we want to accommodate that increased demand without reinforcing the transmission and distribution or additional generation, we can do something to reduce this peak demand or accommodate the increased demand with this same peak demand. Then it will be a very good, it's a win-win situation. So that is a technique which we call as demand side management. The aim of that demand side management is to ensure this, to defer investment in transmission, to accommodate the increased demand or even reduce the peak demand. So this is the typical all India curve. So over entire year, if you will see, you will come out with this. So here we have a morning peak, evening peak, night lean, because night even residences, industrial consumption, that will be less. Some industries will be there, but others, mostly residential, even commercial complexes, all these will be commercial residential load will be very less. So we have a night lean, then day lean is there. So you can see this only for this 3 or 4 hours. We have to keep such a high install capacity. So if by certain arrangements we can reduce it a little bit, then we can save a lot of cost. That is the aim of demand side management. So we want to maximize the economic benefits and minimize the power imported from the main grid. So this is for distribution system. So if it can be self-sufficient with the increase, let's say we have sufficient number of distributed generation, solar or wind penetration and storage, then the power requirement from the main grid will reduce. So just as that example was given in the lecture of IITR distribution system. So they have 2.8 megawatt of solar PV rooftop solar PV in over all these hostel buildings and departments. So 2.8 megawatt, and the peak demand is around 8 megawatt. So this much is already generated by the renewables. So if we can reduce this peak demand, we can minimize the power input from the main grid and maximize the use of renewables. So this is also an optimization problem. So here it can be single objective or multi-objective. So here we have two entities. One is the utility and another one is the consumer or customer. So if utility wants to do something, for reducing the peak demand, what would utility want to do? So if utility wants to reduce the peak demand, what would utility want to do? Anyone?
To charge as per TOD, sir. Time of the charges to be increased.
Charge? Sorry, I could not get.
The charges were as per time period, charge will be more, like the TOD charges will be increased.
Yes. So time of use tariff is there. It would want to curtail the load if required, but that the consumer would not like that. So single objective would be, so we have two entities, so utility and customer. So if you want to maximize the benefit to utility, the customer may not be benefited by that. And similarly, if you want to
incentives to customers, sir, to use the power in low demand period.
Yes. And similarly, if you want to maximize the benefit to the customers, the utility may not benefit. So here, either one of them will benefit. So other will not be benefited that much. It will be at loss. But in multi-objective, we can try to maximize the benefit of both. We can give a weightage to both. Both can be, the overall benefit can be divided between the two. And do you want to say something, Anupam?
Sir, how utility and customer both have benefited in multiple objective functions, sir.
And so let's say I will give another example to make it understandable. Suppose we you would have heard of this mutual funds, right?
Yes, sir.
In mutual funds, we have different types of. There is one option of systematic investment plan (SIP) that we call, and in that we have different types of different options. So you have one where you will get very less. Will get They will invest in debt, and you will get a return, a fixed return. But there is no risk associated with it. Return is less, but there is no risk. Another is they will invest only in stock. So their return is high, but the risk is also high. And there is one in between balanced. So there they will invest in both debt and stock. So return will be in between, and risk will also be less. So here we have two things. One is return and another is risk. So if you want to increase the return, risk is also increasing. But no one wants to increase the risk. So we want to increase the return also, but reduce risk. So these two are conflicting in nature. So similarly, here in multi-objective optimization also, if utility wants to suppose this, let's say this is only the so this is the let's say this is the curve, and now utility wants to change this curve. Let's say this should be the curve as per the utility. And customer wants another curve. Customer wants this type of curve. Even at peak demand also, it does not want to shift the load. Utility wants that. So if we go only with this red curve, then customer will be at loss, because customer will not be willing to do that. Correct? So if you do only this one, then it will be single objective for utility, which will favor utility. If we go only with this red curve, sorry, this blue one is for customer. If we go with only with this red curve, it will be utility. But if you try to maximize the both, you will try to match the actual curve with both of these. We give a weightage to them. Let's say we have one parameter beta into utility. So this is our actual demand, actual curve, and this is the desired curve, beta minus 1 minus beta into customer. So if beta is 0.5, both will be equally benefited. So we want to minimize this difference. This difference should be as minimum as possible, or it can be 0. So by varying this beta, we can change who would benefit more. We can make it 0.5 also, both will be equally benefited. So that will be the solution which will benefit both of them. So
Thank you, sir.
So the resultant curve will be somewhere in between this red and blue curve. So the resultant curve can be somewhere Can be somewhere like this. So both are benefited here. There is one more example which I can give. So suppose we want a planning problem is there. We want to plan for transmission system for future, and we want to minimize the investment in transmission. So to consider the uncertainty in renewables and everything, we take expectation over all the uncertain variables. So that is, we have two components. One is expected cost, and second is risk or variance in that cost. So let's say this cost has a distribution like this. It has a mean value, mean cost, and there is some standard deviation. So considering different, because in future we don't know what will happen, so we will take different values for generation, for demand. So there will be different cost. So if we take the mean value, it will be expected value, and there can be some deviation. So which we call as risk. So I'm using same beta 1 minus beta. Okay, and we want to minimize this cost. So we want to minimize the expected cost as well as risk associated with it. So if I take beta is equals to 0, then it will try to minimize the risk. So it will try to make this gap as low as possible. But if you want to minimize the risk, what will happen? Cost will increase. Similarly, if I make beta is equals to 1, then I will minimize this mean cost, but there is no guarantee that risk will not be there. There can be lot of risk. The variance can be very high. So we can take beta in between something. So we will also take care of expected cost and risk also. Because both these beta is equals to 0 and beta is equals to 1 will give different solutions. They will result in different requirement of transmission lines. So how much risk we want to take will decide the number of transmission line we have to build. Is this clear?
Yes, sir.
Okay, so next thing is there's different types of strategies for demand side management. So first one is peak clipping. So here we are reducing the peak demand itself. So here what will happen? Peak demand will reduce, and also the overall area under this red curve. Now it has become this curve. So area under the curve, the overall energy consumed will also reduce. So this can be done by using efficient devices. What we did by shifting from CFL to LED was this, reducing the peak demand. Our energy consumption also reduced and peak demand also reduced. Then next one is valley filling. So in valley filling, we are trying to increase the load during off-peak hours. So in this case, what will happen? Peak demand is changing or not? So in every case, we have to check two things, peak demand and energy consumed. So in this case, what is happening with peak demand and energy consumed? Are they same or increasing, decreasing? So what is happening with peak demand in valley filling? Is it same? Is it increasing or decreasing?
Valley filling energy will be increased.
Correct. Energy consumption will increase because we are increasing the demand in off-peak hours. But what will happen to peak demand?
Peak demand will be reduced in both the cases.
No, in this case, we are not reducing peak demand. Peak demand is still same here. We are just increasing the load during the off-peak hours.
So as per the diagram, you are shifting the load. Peak, you are given a bar on top.
Sorry?
That you are shifting that load. You are shifting that peak load to other load demand time period.
that is happening here in load shifting. We are talking about this valley filling.
Okay. Valley filling, it will not be there.
Yes, correct.
Demand will be more.
Correct. So peak demand is same, but energy consumption is increasing here. So this we can do by shifting electric vehicles. We can charge electric vehicles. The new electric vehicles which will be coming, if they charge during the night time, then this will happen. And third one is this load shifting. Here is the thing which you were saying. So here what is happening, peak demand is reducing. But what is happening to energy consumption? Energy consumption
Yes, energy
is same, right?
energy consumption is more than that of peak living, but less than that of valley filling.
If we take only, consider only load shifting. So before load shift, if we consider only the red curve. So this was the original curve. Green curve.
Same energy. Yes, same energy.
Energy consumed will be same, sir.
Comparing red with the green curve. So it will be same. Energy consumption is same. We are only changing the peak load. We are shifting it to the off-peak hours. So this will reduce our peak demand. But area under the curve remains same. Then the conservation mechanism. So here we are doing strategic conservation. We are reducing the load in such a way that the load shape remains same, but overall peak demand and energy consumption both will reduce in this case. So can you give an example of this kind of thing? How we can do this?
Using energy efficient equipment.
Yes, that is one thing. Another? Yeah, that is a most the easiest way. We can use, if we use efficient everything, we make these green buildings. We have good ventilation. Then we will require the cooling requirements will reduce. We can use efficient motors and all these things. That is correct. Then this strategic load growth is opposite. Exactly opposite. So we are trying to increase the load in such a way that load shape remains same, but overall peak load and energy consumption is increasing. So suppose new area development is being happening, or new electric heating or cooling requirement is there. So that we can do, or industrial electrification which is going to happen. Then last one is this flexible load. So load shape can be changed in any way. So this, the way we want, we can do that. Utility. So these demand side strategies are mainly they will be done by the utility side. So now we will see this. These are the different demand side management strategies which the utility can use. The first one is the energy efficiency. These, you can replace the less efficient equipment with high efficiency equipment like CFL to LED. This now you would have heard of these BLDC fans. Have you seen, or are you using these BLDC fans? Ceiling
Yes,
fans.
sir. Now, all the state public sector, central public sector are going for PLC.
Yeah, so earlier we were using these induction motor based fans. So they were consuming at least 70 watts, 50, 70 minimum. That was the minimum requirement. But now these BLDC fans you can use at 25 watts. 28 watts BLDC fans are available. So they will consume less electricity. Then energy conservation is another. So here we can do, what can be done? Utility can encourage people to change their behavior pattern. It's difficult to do that. But energy consumption, simple things that switch off when not required. These are but it's difficult to do this. Then third thing is demand response, and this can be of three types. One is control strategy based. So it can be centralized or decentralized. So in centralized, all the consumers will be communicating with the main operator or aggregator. And in decentralized, they can communicate both with the aggregator as well as with the other neighbors. So there is one concept of peer-to-peer trading. So that can be done. So one house can communicate with the neighbor house. Suppose one house, the demand is more, requires more power. It can ask the neighbor. If it has excess demand, it can provide to other, stored in its battery or energy storage or electric vehicle. It can supply to the other house at the peak hours, let's say. All these things are possible. Then second is price based, and in price based also there are two: dynamic price based, and second is incentive and penalty based. So in dynamic price we have time of use tariff, which you were talking about. So we can have different price at different times. Let's say we have two division, peak hour and off peak hour. So in peak hour we can have high price, and in the electricity market it happens. Although at consumer we always get our government state electricity boards, they have fixed a price which they may increase over 2-3 years, but over the year it remains same. But what the price at which they are buying from the market, that is not constant. If you will see the data on IEX or other the power exchanges, then you will see during peak hours the prices are quite high as compared to the off peak hours. So that is because of this. So right now we don't have in India the consumers they are priced at same level throughout the year. But if we implement this time of use tariff, then during peak
No,
hours,
sir. For industrial consumers, COD charges are there, sir. Off peak and peak
yes, that
periods
is
are different.
correct.
For domestic purpose, it is not implemented, sir.
Yes, that is correct. For residential consumers, we don't have it. For industrial, even commercial consumers, we have it. It is correct. So if for residential consumer, if we do it, then people would try to shift it, but that is also a difficult political issue. So it's difficult to implement, but that can happen. Next is critical peak price. So here, the peak price, we have a price, but even within peak hours, few hours are kept as critical peak hours, and during that time, prices can be very high. So this is to further discourage the consumers to use to shift their demand from that critical hour. So they can switch off their non-critical appliances during those critical peak hours. And then third one is the real-time pricing. So it is same as whatever market price is there, we can use the same. It's very futuristic. Then another one is incentive and penalty based. Some noise is coming. So the next one is this incentive based penalty and incentive and penalty based. So here the consumers will be penalized or they will be given incentives if they follow the directions of the utility. So if they agree that on the request of utility, if they agree to curtail some of their load, then they will be given some incentives. And this third one is the demand bidding. So here demand can bid to curtail their load. This is even market at the retail side, consumer level. That is also, it's a very futuristic thing. But all these things can happen. So that require awareness also on the part of consumers. That is very important. The third thing is load based, which is one is task based and energy related. So can you tell difference between the task related and energy related? Demand response. It is the description is as per the words which are used here. One is related to the task which is being performed. So here the task will be same, but it will be delayed. So energy consumption here will be same, but it will be delayed. The time of operation will change. But in the energy related case, the energy requirement itself will be reduced, but the time of operation will not change. So can you give example for energy related demand response where we can reduce the energy requirement but we will still operate the equipment?
Like suppose there is a temperature rise. So at that time, our consumption of ACs and all will increase. So their temperature setting, also will reduce. But if the temperature is okay, then we can set our AC to say suppose 27 degree. So AC is on, but temperature setting will enhance the increase or decrease the electricity requirement, energy requirement.
Correct. This is true, and this is very practical. By changing the temperature setting of the AC by 1 degree will not create much impact. It will not even notice it. So that's a very practical example, and that is being done. That is done. So these, especially in these commercial complexes, these HVAC, these AC air conditioning, they do that. They will reduce the temperature by 1 degree. You will not feel it. But that 1 degree reduction in temperature will lead to a significant reduction in the demand. It's a very good example. So let's take questions now. So which of the following statements user are correct with regard to optimal PMU placement and distribution system? First one is PMU installation is highly economical. Then observability constraint is an essential part.
B is the answer. B.
B. Correct. B is correct. So particle form optimization is not a classical optimization technique. It's a meta-heuristic technique. And PMU installation is not economic. So these are the differences which I was talking about. So why do we prefer classical optimization techniques? Can anyone of you tell?
They are matured and their computation power is less required.
Any other advantage?
They are matured. That is the best example.
Even the genetic algorithm is quite mature. We have been using it for many decades.
But their computational requirement is more. Computational requirement is more for generative work.
It will depend even for MILP formulation computation for a large system. It becomes very difficult. Computation requirement becomes quite high. One of the main advantages that these classical, these anti-heuristic techniques, they do not guarantee global optimization, global optimal solution. Suppose we have this kind of function. So here we know there is only one optimal solution. Whatever technique you use, you will easily reach here. Whatever initial condition you give, you will reach here. But if the solution, if the function is something like this, then it will be very difficult. If based upon initial condition, if we give an initial condition of this as the initial condition, then it will reach here. So initial condition will determine the solution also. And the main advantage of using this, especially for power system, that's why we are using DCPF also, because the DCPF results in convex optimization problem. And convex function means these type of functions. So any function for which if we draw a line between any 2 points, that line will always remain above that function between these 2 points. So this line is always above this function. So it's a convex function. And for convex function, it's a property of convex function that there will be only one global optimal solution. And that global is local. So whatever solution we get, it will always be a global solution, global optimal solution. So this DCPF, linearized DCPF, leads to a convex problem. And if we use these techniques, MILP, LP formulation, we will get the global solution. And
so classical will give global solution, you want to say?
Yes, for convex problems. So that is why there are several DCPF formulation is a convex formulation, and there are some convex relaxation for for ACOPF also. So they relax it to form some convex problems, and we have solvers for these convex problems, and we can solve and get the answer. Although the answer for actual AC and the convex relaxation will be different. But why do we use DCOPF is that, especially even in market clearing or day-ahead real-time market clearing, we use DCOPF only, because DCOPF it gives solution in one shot. It's very quick. We want to clear market for next 15 minutes. We cannot wait for 1 hour for the solution or the optimizer to solve the problem. We want quick solutions. And that is why we use DCOPF in markets. Although the optimal solution will be something else, but that will not impact much, because actual operation of our system is being monitored. Our priority there is to have a quick solution. So we are using DCOPF there. So even for planning problems, DCOPF is used at present. So we always want the optimization problem which we are writing, it should be, if it is convex, then it makes our life very easy, because we have standard solvers which can solve these problems. And we also want to avoid these integer variables or binary variables, because for a large system they create problems. The computational burden increases. If the problem is linear LP problem, then it's very easy. The moment we introduce integer or binary variables, then again computation requirement increases. And if it becomes non-linear, then it becomes very difficult. Then there are no standard solvers. We have to use problem specific. We have to write algorithms. And they are also governed by these initial conditions. So it's better to use whatever algorithm meta-heuristic techniques if we are using, we should compare it with one classical approach. That can give us confidence that the output which these meta-heuristic techniques are giving us, they are correct. So this, in PMU placement problem, we have a binary variable or integer variable. And what is that variable? Can you tell? We discussed it.
We have integer as well as binary both.
How?
Suppose some utility is on and off, so that is binary only.
Yes.
And like battery is charging or not charging, so it is binary.
Yeah, so the formulation which we saw at the beginning of the session, so that is for PMU placement, and there the X variable is whether the PMU will be installed on that bus or not. So it's a binary variable, 0 or 1. Similarly, in planning problems, we have transmission line, whether the transmission line will be there built or not. So that is also a binary variable. But suppose if you want to do optimization for these OLTCs, online tap changer transformers. So they have taps. They have discrete number of taps. Let's say 25 taps. So now which tap should be chosen? Now it becomes an integer variable. 1 to 25. Each transformer tap can choose a value between 1 to 25. So in volt var optimization, we use these VLTCs for reducing this, keeping the voltage within the limit by providing the reactive support. So that it becomes an integer variable. Is it clear? And these, yes. So,
The power system problem is both binary as well as integer problem.
yeah, there are different types of problems, and depending upon problem, the variables can be binary also and integer also. And in some problems, we can have both also. So if the problem, so the standard problem is like, we write it like this, any optimization problem, minimize g of x over x. X is the variable here, subject to let's say F. So these are equality constraint. So these are similar to our nodal balance constraint. We say injection is equals to the withdrawal. So these are those constraints. And these are inequality constraints. So can you give example of these inequality constraints?
Generator capacity is inequality.
Yes, generation limit, line flow limits, voltage angle limits. So whatever limits that bounds we put on any variable, then it becomes an inequality constraint. The equality constraints are, so if this g, h and x all are linear function, and x is a continuous variable, then it becomes a linear program. And if any one, at least one of the variable, if it becomes binary or integer, if it becomes binary, then it becomes binary problem. So in general, we call it integer problem only, because binary is also an integer, 0 or 1. So we call, if any one, at least one of the variables, if it becomes integer or binary, then we call it MILP. And if all other objective function constraints are linear, then it becomes mixed integer linear programming. And if any of the constraint or objective function becomes non-linear, then it becomes non-linear programming. And if integer variables are there, then it becomes mixed integer non-linear programming. Is this clear? If you have confusion, you can ask.
Sir, what is a convex problem? You told that, sir, for classical method, it gives solution for a complex problem, dual solution. So what is, sir, actually convex problem?
So convex problem, any linear problem is a convex problem, because so this is the general notation for any objective optimization problem. So if gx is a convex function and the set constraint consisting of these constraints is a convex set, then that is a convex program. So any convex function.
Is there any concave program also?
Concave is opposite of it. So if you want to minimize cost, then it will become maximize of minus cost. So it is opposite. But we generally, even if there is a max problem, we convert it into min. We multiply it by minus and we convert it into minimization problem. So that is a convention that we are following. We use it. So max problem we can convert it into min. So all the solvers are written in that way. They minimize everything. So max problem they will convert it into min problem first. So here this is convex problem and this is a concave problem. So we convert it into convex. Just multiply the objective function by -1. It will become, so if it is minimization of fx, and if I multiply it by minus, then it will become maximization problem.
Yes, sir.
Okay. So, and these all meta-heuristic techniques, all these are nature-inspired techniques. Genetic algorithm, particle swarm, and there are so many. Stingray, gray wolf. One is teaching learning-based optimization, and that is based upon this interaction of student and teacher in a class. So there are several examples of that. And genetic algorithms I think it's the oldest first. So let us move to the next question. Which of the following is correct with regards to cyber physical system? First, actuator and sensor are part of cyber layers. then communication latency is a major advantage. And
Sir, slide.
which one?
Question slide, sir.
Sorry, question?
B is the answer here.
Yes,
sir?
B is correct.
D is the answer.
Yes, because one of the ways to update our system. Always keep updated version of firewalls, VPN, and keep our softwares up to date.
Sir, is slide changing means I am not seeing question on the slide.
Sorry, your voice is not clear. I think your network is here's network problem. So this is the next question. Which of the following are limitations of demand response for frequency support services? Unpredictable demand response, complexity involved in communication, total amount of flexibility provided does not entirely compensate for substituted conventional synchronous generator. And 4 major ancillary services cannot be provided simultaneously by demand response, or all of the above. Which one is correct? So demand response is also one of the way to provide frequency support services or even inertial support. Because if we are reducing the demand, then in a way we are providing inertial support. If frequency is reducing, what should I do? I should increase the demand or reduce?
Increase the demand.
Yes. No. If frequency is reducing, I should reduce the demand, no?
Or we have to feed more power.
Yes. So here, because we are talking about demand response, so here we can either increase or reduce demand. If frequency,
Reduce the demand.
sorry.
Reduce the demand.
Yes. So frequency, if frequency is reducing, we can reduce the demand. So that will help in maintaining the frequency. So which one is correct in this case? What's the answer?
Option E.
Yes, option E is correct because it's difficult to predict because we don't know consumer behavior. We don't know how they are going to behave with respect to the price signals. We don't know. And for ensuring demand response, for frequency support services using demand response, we need communication. We need bidirectional communication. And also, we cannot it cannot entirely compensate because there is a limit to how much demand can be reduced using demand response or increase. So it cannot compare with the conventional synchronous generator. And also it cannot provide all these services at a time. So E is correct. Next is select the correct option with respect to frequency support services. So tertiary frequency response is based on governor action. Interconnection frequency deviation can result in load shedding. Energy storage cannot provide frequency support services. And response time for primary services is within 2 cycles.
B is the answer. Primary frequency.
D is not correct, I think. B should be correct. D is primary frequency services will respond within seconds. And one cycle is 20 millisecond. Millisecond range Only inertial support can provide. So here we can see we have these 4 types of frequency response services. First one is inertial support, which is order of cycles. So we talked about it. So inertia, inherent inertia, it can quickly provide that variation in the load. So it is stored a rotating energy. Same principle, which energy storage using the same principle as this inertial support services? Can you tell? There is one mechanical energy storage which uses this concept.
Flywheel?
Flywheel,
Yes,
sir, flywheel.
correct. Flywheel. Flywheel. So flywheel can provide this inertial support. So it is accumulation of inherent response of conventional generator that arrests the frequency decline. So it can be provided by this virtual inertia also. So this is in the in orders of cycles. So one cycle is 20 milliseconds. So 2 cycles, within 1-2 cycles it can work. Then next comes, if the frequency is not arrested by this inertial support, that means the load, the deviation is much more, and we have to move to the primary frequency response. And it is also automatic. So it is based upon the droop control and governor response. Based upon the droop characteristics, the load increase or decrease will be distributed among the generators, all the parallel connected generators, and the frequency will be it will be restored to a common value. It may not be the same. It may be same also. It depends. So it may, but it will result in a one value. It will, all the generators will operate at one frequency. Droop characteristics which we have seen last week. It may include automatic load shedding. So it is fully automatic, and this happens in order of seconds, 2 to 5 seconds. Now these two are not automatic. So these first two do not require any kind of communication. No communication is required here. They will operate on their own. At the secondary and tertiary, they require communication. And so once, if the primary is also not able to arrest the frequency, then secondary will come into picture, and it will also replenish the primary reserves. So it will return the frequency to the nominal value, and it will minimize the area power mismatch. If two areas are connected with each other via a tie line, or two microgrids are connected with each other via transmission line, when we connect two areas, and the interconnecting line is called tie line. So variation in generation demand in one of these areas will affect the another one also. So that area power mismatch is taken care by this secondary frequency response, and this is through this centralized automatic governor control, AGC control, and this requires communication, and it has to respond within 30 seconds, and it has to respond up to, so between 30 seconds to 30 minutes. Then after that, tertiary response will come into picture, and they are taken care by the spinning and non-spinning reserve, and this is not at all automatic. The operator has to call the generators or send a signal. They have to intimidate them. So what is spinning reserve? Can you tell? We heard of this term, spinning reserve. Why is it called spinning?
They are the generators which are not they are rotating unsynchronized, but they are not feeding the load to the grid. So once it is required, then only they will feed the load.
Yeah, they may be they may even be producing. Suppose a generator is there 500 megawatt, so it may be producing some 400, but remaining 100 megawatt it can provide for spinning reserve also. So that is also possible. So that is correct. What you have told is absolutely correct. So they are spinning. That spinning term comes from the fact that they are synchronized to the grid, but they are not generating. Either they are not generating at all, or they are generating, but still they have a buffer which they can supply for reserve requirements. So the tertiary will try to restore the frequency also, and it will try to replenish the secondary reserve also. Yes.
So then what is the non-spinning reserve, sir?
Sorry, what is?
Sir, you have told about spinning reserve, then what is the non-spinning reserve?
Storage will come in non-spinning reserve. Energy storage.
Storage of what?
Energy storage.
Like what?
Then diesel generators can come into non-spinning reserve. So they are not.
They are not synchronized.
Yeah, they are not synchronized. But they can immediately do that. And also they have time, 15 to 16 minutes. No? They have 15 minutes time to even synchronize them. Even gas-based generator can do that.
Pumping storage also.
Pump storage, yes, correct, absolutely. That is also true. Pump storage can also do that. Correct. We have pump storage plants operational. Several pump storage plants are there. So they help in these providing reserve services. It's a good example. Yeah. So next question is, which of the following is not an aim of demand response analysis? Minimization of total consumption, elimination of line overloading, promote conventional source generation, reduction of total required power generation. So which one is correct? Which one is not an aim? So it's not. Yeah, see, we don't want to increase the conventional power generation. We want to reduce. But others are true. We want to reduce line overloading. So if we can manage to shift our load in such a way that we can reduce the overloading of lines, and we want to reduce the total requirement from the main grid also, and minimization of consumption. Yeah, so these are the aims. Minimization of electricity cost, social welfare, aggregators power consumption. Both of these are both minimization of social welfare and aggregated power consumption. So these are different types of objectives which can be used for demand response analysis. Is it fine? Okay. Next question is, which of the following is a desired goal of an utility? Peaky load curve, flat load curve, high peak deficit, less off-peak load, or none of the above?
B, flat load curve.
We want a flat load curve. Although that is ideal case, but we want close to it. We want to reduce the peak load. That will increase the efficiency of generation and the load factor. And overall install capacity requirement will also reduce. Which of the following is correct with respect to demand side management? Load shifting strategy is more reliable compared to other strategies. Multi-objective strategy provide more peak load reduction. And demand side management using DC microgrid with Energy storage is an effective solution to feed the load during peak hours in the present distribution system.
All is the answer. All.
Yeah, this question is based upon the case study which was there in the lectures. So using DC microgrid with energy storage, we can feed loads during peak hours. And also it was shown that multi-objective strategy provide more reduction of peak load. And this is also more reliable because we are simply shifting the loads. We are not curtailing load. Energy requirement is still same in load shifting, but we are simply shifting the peak load to the off-peak hours. Which of the following are communication requirements for demand response? Quality of service, interoperability, scalability and flexibility, and security.
All. E is the answer.
Yes, E is correct. Option E. Energy related demand response alters both the operation time of flexible load and consumption, alters the operation time, alters the consumption during peak load, or none of the above. This we have discussed. A, B, C, or D? It's energy.
Consumption during peak load.
Yes, correct. Alters the consumption during peak demand. Energy consumption will be changed here.
C is the answer. C.
Yes. Which of the following is not a dynamic pricing based demand response? Time of use, critical piece, peak pricing, or reactive time pricing.
Reactive power.
Correct. Reactive type pricing. Yeah, so questions are over. So do you have any doubts? I think today I've exceeded the time limit. Sorry for that.
Thank you, sir, for giving us extra time.
Thank you.
I should thank all of you because today is a holiday and you all still came for the session. So that's very
Thank you, sir.
encouraging for me. Okay, so we'll meet next Tuesday then.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Ganesh Chaturthi also. Thank you.